Thank you all for coming to the first, I guess, inaugural DDC 2020. I wanted to start this conference off by giving a special thank you to both HP and NVIDIA for sponsoring the event and providing guidance on how to run conferences like these. Also wanted to give a special thank you to Sean, Sarah, Lee, Diego, and Rachel for honestly scrambling together and putting this together. So thank you all for joining, and I hope you enjoy. So my name is Harshil. I'm the CEO of Dendrite, and my goal today was to kind of talk a little bit about the industry and talk about what really is the future of additive. Now, I know this is a very big and philosophical question, but the idea was to try to break it down into small bite-sized pieces and to try to understand where the industry is going and try to offer my perspective. So before we can really think about the future, I think we need to think about the past. So let's go back all the way to the 1980s and print like we were printing then. So back in the 1980s, for those who remember, we had these things called dot matrix printers. They were all the rage, and they functioned by using pins and wires to basically stamp graphics onto the page. So in the 1980s, dot matrix printers were popular. But around that same time, a company named Adobe was founded. It was founded by a mathematician named John Warnock, and they essentially instantaneously started working on something called PostScript. PostScript was and is essentially a method of taking an electronic page or piece of data and converting it into instructions for a printer. Famously, Steve Jobs convinced Adobe to adapt PostScript for the Apple LaserWriter and essentially kind of sparked the desktop printing revolution. Before then, we had all kinds of printers. We had all kinds of software that wasn't necessarily compatible between them. And honestly, the printers themselves were fairly cumbersome. So what about PostScript was important? So there's quite a few things when you consider PostScript, but I tried to distill it down to essentially 4 key qualities. The first quality is it required computer hardware, namely the Motorola 68000. So essentially what we're talking about is a piece of software and a piece of hardware being unioned in order to create a better print quality. So PostScript as a computer language basically used to take in this raw geometric data, compute it on the fly on the printer, and output printer specifications and code. Next, the key aspect of PostScript is the fact that it was universally marketed to all the printer companies, regardless of which brand, right? So whether it be HP, Epson, you name it, we had this unique industry-wide language that was being applied kind of across the board. But taking a step even further back, why even have PostScript? So PostScript itself actually enhanced the print quality. Back then, when we were considering dot matrix printers, right? Text on a page was actually difficult. PostScript enabled folks to be able to print splines and fonts on a page. And the key here was the on-the-fly printer instructions. You'd be able to take spline data, send it to the machine. It would do something called a RIP, raster image process, and then send that to the actual printing device. And then finally, PostScript itself was an interpreted programming language. And the idea of being able to take geometry and convert it to a program was already prevalent in the 1980s. So given that these are the key 4 aspects of PostScript, and this is what caused the desktop printing revolution, my goal was to see how these things are kind of analogously translating to modern day times. So the real question here is history going to repeat itself? Is the future of additive essentially what happened in the 1980s? So focusing on specifically the computing aspect, one conclusion that I came to was the future of additive is computing at the edge. So what does that really mean? So if we take a brief history at CAD, CAM, geometry kernels, you'll see that quite a bit of development happened in the 1980s, not only in 2D and PostScript, but also on the CAD, CAM side. A lot of 2 kernels were made, namely Parasol and ASUS, and a number of companies were formulated all the way leading up to 2000 when NVIDIA released the first GPU. This should be astonishing because essentially the majority of modern CAD/CAM technology was built in a decade that didn't have GPUs and did not have modern computer architecture. And by modern, we're talking about going from kilobytes and megabytes of memory to gigabytes of memory, and going from one, core with, clock rate in the megahertz range to thousands of cores in the gigahertz range, right? So essentially, computer architecture and hardware has dramatically changed over the last 30 years. So it's safe to say that from a 3D computation and geometry standpoint, we're actually kind of stuck in the past. Even now, when we're talking about, for example, GPUs, we're not really using them for computational geometry. We're actually using them for rendering. And that honestly is a travesty. This is further compounded by essentially these three key printer scaling laws. So I have a hypothesis that your printer is going to become a supercomputer. Why is that the case? Well, every single build volume that we've seen over the last 5 years has been increasing, slowly but surely, right? This means that data is increasing at a cubic rate. Beyond that, the machine precision is also increasing, right? We're starting to see things that are going from 40 microns to 30 microns to 10 microns to even 1 micron. Again, data is going to scale cubically. And then beyond that, the machines themselves are becoming monumentally more sophisticated, in that you're able to control different chemicals that are being jetted onto the powder, or being able to control the different laser speeds and feeds. Again, the number of parameters is exploding, and that only compounds how much data is going to be required to run these machines. But all is not lost, because interestingly enough, even though Dennard's law and Moore's law is sort of trailing off in the CPU land, in GPU land, everything is still on pace and skyrocketing. In fact, you'll notice that this graph here is actually on a log scale, meaning that theoretically at this point in time, one of the key technologies that could potentially handle this explosion of data is namely a GPU. This is interesting because, similar to PostScript with the Motorola 68000, we now have another analogous chip technology which may be useful for printing. So again, let's ask, is history going to repeat itself? And let's now dig a little bit deeper into toolpathing standards. So again, we've seen a number of folks coming together. This is, for example, a picture of the Dyndrite Developer Council. And the whole idea here is we created this council initially for A, for people to scream at us to tell us what we're doing poorly, but B, honestly, to bring the community together and create a standards body. And the whole idea here is, can we create one unified standard to go pull all of this together so that the end user has a better experience? This mirrors, again, PostScript in the perspective of A, better prints can be potentially improved by using splines or zoning, basically having different types of parameters depending on where you are within the slice, and by sophisticated parameter control. But again, the key to all of this actually even happening is making sure A, we're using modern compute, and B, making sure that the industry is setting a standard. We can't possibly have 30, 40, or 100 separate printer companies, all with different competing standards, and then trying to have separate pieces of software for all of them. So the future of additive is hopefully consolidation from a software and standard standpoint. And again, with the toolpaths, you'll see Steve talk about this in more depth later today. So what else? So in order for history to repeat itself, the future of additive has to have some element of automation and production. So again, what does that really mean? So production can only happen by abandoning the past. And there are three key things here. Number one, meshes. Meshes, or STLs, are pathological to fix. So it stands to reason that in order for us to have an automated or production workflow, we can't lose all of our momentum in our workflow by constantly having to check in to make sure that the geometry that we're bringing in is correct or not, or not dirty. Beyond that, the designs are only getting more and more complicated. Right? We're seeing more and more complicated rocket parts, heat exchangers. We're seeing the advent of topology optimization, and it's kind of exploding. And quite honestly, having that juxtaposed against the mesh only means that the mesh is only contributing towards this data explosion problem. Beyond that, in order to hit production or automation, we have to recognize that the GUI is for learning and prototyping, which was awesome for the last 30 years. But if we're going to start to print thousands and thousands of parts, all unique and different, then we need to put it on a server and crunch those numbers. And then finally, we have, again, the advent of our data problem. We're seeing 10 gigabyte CLI files and 4 terabyte PNG folders. And quite honestly, that's not practical or smart. We need a piece of software or a system to on the fly expand this manufacturing data. In fact, we've actually run into various printer companies who, when all is said and done, would essentially have to spit out about 4 petabytes of data if they were to specify it all the way. To put that into context, if you had a computer and you had it Ethernetted to the printing device, it would take you literally 0.1 years to send that data over that Ethernet. Clearly, that doesn't make any sense. And there needs to be a way to expand that data on the fly, and honestly expand that data closer and closer to the edge, namely the printer. So finally, how again could history possibly repeat itself? Well, I believe honestly, the future of additive is also a dramatically changing demographic. And I bring this from my personal experience. So I taught the MATLAB and Python class at Berkeley. And the one key thing I realized was today's engineers and technicians are all graduating with some form of programming or scripting experience. This doesn't mean that everyone is necessarily a programmer or is going to go have a software job, but it does mean that modern day folks in this industry are going to have some basic experience with programming. And so here again is where the PostScript analogy kind of gets interesting. If we were to go make PostScript again in a modern day time, we would want an easy to learn interpreted high level language for general purpose compute, and hopefully it would fit into a large ecosystem. Enter Python, which actually meets all of those qualifications and those requirements by definition. So you may be wondering, so what really is the future of additive, right? And so to summarize, if we're gonna kind of learn from the past and bring that to the future, PostScript depended on a chip, namely the Motorized 68000. If you agree with this, then the future of additive probably also is gonna depend on a chip, most likely the GPU. A technology needed to be created that was printer company agnostic. Again, similarly, a technology needs to be created that is process agnostic. The data needs to be computed on the fly, right, in PostScript so that you can get those nice fonts. And again, the data needs to be computed on the fly in additive because otherwise we're going to have a data explosion. And finally, hopefully that language, that technology is interpreted so that it's easy to code against and script against, which means that hopefully the future of additive involves Python in some way, shape, or form. So the punchline to that is essentially why we created Dendrite. And it may have been sort of a self-fulfilling prophecy, but the idea was, let's build a kernel that is GPU accelerated, that has a Python API scripting interface, and is printer agnostic. Right? So the idea here is we're hoping that lots of folks are going to try to build interesting applications on top of Dendrite. As I mentioned, we have a Python API, we're GPU accelerated. But I think the key to all of this is the last two bullets, namely folks being able to protect their IP and not having to reinvent the wheel. There's no reason that anyone should reinvent how to go rasterize a slice or create paths or polygons and Boolean them, right? That should be something that is handled agnostically across the board for all technologies. What folks should be really concentrated on is building a build processor, building an MES system or a topology optimization system, or honestly building a toolpathing post for their specific printer and process, right? And the whole key here is we're trying to basically be the best mathematicians in the room and provide a way or a toolbox for folks to innovate and build on. So kind of to summarize, I think quite a few things are going to change in the future of additive. I think the fact that the manufacturing hardware has outpaced the software is about to change, and we're about to see all kinds of new and interesting software innovations across the board. I think that The design of the current things that we're seeing right now is also going to dramatically change over the next 10 years, simply enabled by these new print technologies and by new software. And then finally, I'm really hoping that folks are going to stop fixing files and switch to the solution that everyone already knows is the best solution, namely stick with your CAD data. So with that, I'm genuinely curious, what will you build? And I'm happy to answer any questions, and I hope you enjoy the conference. Thank you.
Thank you, Harshil. That was a great presentation. All right. So to start Q&A, let's take one from Johan Lamens. Are you transforming geometry into a PostScript program or specify geometry as a PostScript program?
So the goal with our kernel is to in order to keep things geometry agnostic, we will always be able to import in STL files or CAD data. And what we're essentially doing is, instead of storing a PostScript format, we're actually converting all the workflows into a Python program. So the idea is we're essentially trying to make 3D PostScript in a non-proprietary way using Python.
Okay. And then, okay, any more questions? From Farco, how are you working with ASTM and ISO about influence in international standards bodies?
That's a good question. So we've been talking to a number of folks, for example, on the STEP committee, and a number of folks in the ASTM and ISO standards bodies. So far, it honestly didn't make sense to go full-fledged to talk to them, but the goal is to involve them in the Dyndrite Developer Council, and that was the whole point of creating the council in the first place. So I'd say not much so far, but that's where we're going.
And then there's a bit of a follow-up question from Terrence. How will this work with an agnostic process in mind? How will this work align to ISO-specific dev?
I honestly don't quite understand that question. I don't understand what specifically about ISO dev is there, so I'm more than happy to answer that question after the fact in the vendor lounge.
All right, please keep that question for later, Terrence. All right, from Rupinder Tara, will your geometry kernel work alongside existing geometry kernels or replace them?
So I think it's going to work alongside existing kernels. This kernel is kind of purpose-built for specifically additive manufacturing at the moment in time. And like I said, we're able to read in Parasol and ASYS files. So by definition, we work alongside them.
All right. So another one from Gregor Wiesgrab, and apologies everyone if I pronounce your names wrong. When I saw you at Form Next, you mentioned that you can't do G code yet. Is this on the list? Maybe clarify that part of the question as well.
Yeah, so by G code, I assume you're angling towards being able to take that raw geometry data and sending it to maybe one of the lower end FDM printers, or maybe one of the industrial grade FDM printers. The idea of being able to take that raw geometric data and do a post on it to create FANUC 6.1, Marlin, or Mach is on the roadmap. We're honestly actually working with a number of FDM vendors at the moment to try to figure out what's the best way to give them that technology.
Thank you, Harshil. All right, and then next question. Would you repeat the time it can take to send a big detailed model to the printer? Did I hear years? So.
Yeah. So I've seen, talking to a variety of folks over the last few years, I've seen, for example, in the rocket industry, I've seen people take, 10 to 24 hours to send data. But the hyperbolic scenario where I'm seeing data explode, I'm seeing literally a tenth of a year, right? We're talking about petabytes of data. And if you, for example, just limit it to Ethernet speeds, that's where that comes from. For example, but you don't even have to honestly wait that long. Like if you, for example, look at the HP machines, if you just do a simple calculation of DPI and the build volume, you'll basically get 4.5 terabytes of data already.
All right, So Rupinder, did you have, I just unmuted you. Did you have any follow-up to that question? Rupinder, you should be able to talk to Harshil. I'm unmuting you now. Oh. Let's move to the next question. Oh, there we go.
No, thank you. Thanks, Harshil. That was great. Got my answer.
Oh, okay. Let's see, next. Can Dendrite be driven from anonymous? All right, can Dendrite be driven by simulation? Oh, where did it go? Oh, can Dendrite be driven by simulation results such as ANSYS for creating custom scan paths for metals?
So that may or may not be one of the reasons why Altair and ANSYS are on our Dev Council. The idea was to create a closed loop way of being able to take simulation and process simulation data and use that to influence scan paths. You'll see that when Steve talks about a toolpathing API, the whole advent of even having a toolpathing API is meant to enable that. So my hope is that A, we're gonna either integrate together in the future with us bringing some of their stuff in or them bringing some of our stuff in. And then moreover, I suspect other companies might build software using both of our stuff to make a really cool software application. But the goal is to allow you to connect this to anything you can possibly think of.
Perfect. All right, and another one from Len Wanger. We've got, what is the size reduction of the ASIS or Parasolid data versus STL files?
So I know Len is talking a little bit later today, but I think that's a bit of a trick question because that depends on at what resolution do you want to create that STL, right? So what is an STL and what is a mesh? It is a quote unquote linear approximation of that CAD data. So the answer could be anywhere from going from 10 megabytes to terabytes, depending on what resolution you want. That being said, I've seen basically 10, 20 gigabyte STL files when in CAD land, they were probably on the order of a few hundred megs.
All right. Thank you, Len. Let's see. Another one from Terrence. Will a process streaming data approach to a printer mitigate the time to deliver the large files?
Yeah. I think there are two approaches to that. Number one is streaming the slice data, to and from, with some kind of a buffer. This is essentially how, movies are streamed on the internet. In fact, if you're doing a DLP or an SLA process, you're literally printing a movie. On the flip side, you could also potentially have our kernel run inside the machine itself and then generate the data there. The key benefit there is potentially, the streaming might have, data interconnectivity loss, or you might actually want to modify the toolpaths while you're printing your part. So both are options.
It looks like, I can't see it in the chat. Joseph asked a question in the chat. If everyone can please put your questions in the Q&A dialogue, I'll be able to get to them. All right. Another one from Rupinder. Will Dendrite make it easier to print lightweighted structures with internal cell structures such as irregular cells or lattices? Please explain how.
So I think there are two ways to view that. The first is, how does that geometry kind of come in? So if you already have designed that type of a structure in your favorite design program, the idea where we would help is, well, this kernel is meant to be a number crunching beast. So when you bring that data into our kernel, we'll be able to process it compared to any other solution. The other option here is you might actually want to natively model some of those repeated lattice structures within our kernel, in which case we'll have even more capability to GPU accelerated slice and process that.
All right, looks like we've got a couple more minutes. Any additional questions? Oh, nope. Oh, here's one from Terrence. How will Dendrite express functional graded material in complex lattice structures?
So designing lattice structures is not really our core key focus at the moment. So the answer is we're not, at least for now. That doesn't mean that we're not going to be changing that over the next year or so. I'd say our key focus right now from a geometry creation standpoint is actually more on the toolpaths. So we're more interested, at least right now, with how to create graded toolpaths.
All right, Harshil, did you have any closing thoughts or additional comments?
I'd say thank you all for joining. I think Steve's going to have a really awesome toolpathing panel later today, and both Carl and I and a bunch of industry leaders are going to be at a panel tomorrow. I hope you're excited for that. I'm going to be here throughout the day. Please feel free to ping any of the staff if you have any other specific questions, or I'm more than happy to answer more questions in the panel. So thank you all for joining, and I hope you enjoy the rest of the day.